Going to the moon was the first step. Staying there is our next ambition, with dozens of international public and private missions setting their sights on the lunar surface in the coming years. But the technologies we take for granted here on Earth, satellite navigation systems like Galileo or GPS, video calls, or even fast file transfer, are very limited on the moon. Since the Apollo program, very few lunar missions have managed to land successfully. We cannot have a sustainable lunar presence without reliable and autonomous communications and navigation. That's why ESA is working with its industrial partners on the Moonlight initiative to become the first off-planet commercial telecoms and satellite navigation provider. Launched into space, 3 or 4 satellites are carried into the moon's orbit by a space tug and deployed one by one to form a constellation of lunar satellites. These relays connect to Earth via 3 dedicated ground stations, forging a data network that spans up to 400,000 kilometers. The constellation's orbits are optimized to give coverage to the lunar South Pole, whose sustained sunlight and polar ice make it the focus of upcoming missions. Moonlight will provide data capacities sufficient to serve these planned and future missions over the coming decades, with a navigation service that enables accurate, real-time positioning for all lunar missions. This is the Argonaut. This, or any lunar lander, could greatly benefit from the Moonlight program. With a simplified navigational subsystem, our lander saves mass, reducing cost and enabling other equipment to be carried. Its position is tracked in orbit and descent with accuracy of just a few meters, sending real-time telemetry and video footage to Earth as it touches down safely in its target area. It completes health checks and deploys its payload, whether that's supplies for the moon base or a science mission. A rover connects to the Moonlight network, either via the lander or directly to the constellation. Navigating autonomously, it saves huge operational costs, collecting lunar samples that can be brought safely back home again. The Moonlight system is designed to be scalable and adaptable. ESA is working closely with NASA on LunarNet, a new framework for lunar communication and navigation standards that ensures compatibility, so our global customer base can use the service for their own missions or deploy complementary technologies that could join and enhance the network. So perhaps before long, you could be using your roaming data allowance on the moon.
Good to see you
Hello.
here again.
Good evening.
Good evening, everybody. Well, as you know, we are starting a very interesting talk today from an expert as part of our master JSNP9. We are finishing for the next weeks, but we have some experts, and today is the time to ESA to come, right? Cosimo, Stallo.
Thank you.
How are you?
Yeah,
Welcome to
fine,
the
fine.
welcome
Yes,
to the
I'm so
JET.
glad. Yes, I'm so glad to take this lecture. I'm so honored to present the status of the Moonlight program and other Luna PNT initiatives related to Moonlight. I'm working at ESA, so I joined ESA June of the last year. Before joining ESA, I worked in Thales Alenia Space in Rome. I was the head of unit on end-to-end navigation system design in domain of observation and navigation Italy. And I followed the projects related to Luna PNT. In particular, I was the system manager of the Moonlight for the navigation part. Then joining ESA, I'm covering the role of the responsible for the end-to-end navigation chain system activities. And I'm resident in EXAT, so in the UK premise of ESA in Harwell, where the program is followed and coordinated. So the Moonlight program office is located in Harwell, so following the communication and the navigation chains of the program. So
Okay, well, you just
yes,
tell
before
everything. I wanted just to introduce the topic of today. You have already introduced it because normally we are talking
yeah,
about navigation in different applications here on the Earth during the master, but today we will be talking
yeah,
about the application of the navigation in the moon, right? That's why you
in the
introduced
moon,
in the moon.
yes,
We are just in the Moonlight project, and you will be focused on the main challenges that we are facing today at ESA level and all on Europe level to make this possible, right? Then, if you are ready,
yes.
maybe you can share your screen and all
I'm
the slides you
ready.
wanna.
Okay,
Yes.
I can share my slides. So I'm okay now. Okay, okay. I put in presentation modality.
Yes. Can see you.
Okay, good. So the talk of today is mainly focused on the topic of positioning on the moon. So Moonlight LSNS means Lunar Communication and Navigation Services. But at the end of this talk, I would like also to show you other Luna PNT initiatives related to the main program Moonlight, because anyway, we are defining a roadmap for all Luna PNT services. So not only around the moon, but also supporting the exploration of the moon surface, and in particular, so also supporting the challenging phase of landing, because as you know, landing phase is very crucial, and in the past, some initiatives failed. I can mention the initiative from the private company from Japan. So 2 years ago, so a lander trying to arrive on the moon surface failed, crashed on the moon surface, and so the mission was failed.
Uh-huh.
So lunar exploration paradigm. So according to a report, Lunar Markets that was published around March 2023 from an important agency, NSR, from US, there are so 400 missions that are planned already for this decade, and each of these missions require anyway their own navigation and communication means, because the scope is to go on the moon, in particular exploring the south pole of the moon, thanks also to the recent discovery of water ice on this part of the moon. And anyway, the south pole of the moon is a sort of gateway to Mars, so also supporting the future exploration of Mars. But anyway, developing an own navigation and communication means for each of these missions is to anyway complex, not only from technology point of view, but also it is not cost effective. For this reason, so from ESA, the main scope about lunar exploration paradigm is to define a dedicated communication and navigation infrastructure in order to support not only institutional missions, but also future private missions. So in this way, boosting the lunar exploration, in particular the lunar economy. What is the ESA roadmap for these services, communication and PNT. So the first step, the step 1, is represented by Lunar Pathfinder. Is a sort of a first demonstrator, so able to establish an S-band communication service and also embarking some GNSS technologies, like for example a GNSS spaceball receiver. So later we will see details, and also embarking a satellite laser reflector in order to support the orbit determination from Earth. But so then we have the step 2 represented by the first generation of the Moonlight system, so with the main scope to cover the South Pole. So, and this system will be deployed according to a strategy that it is foresting an IOC phase, so the first navigation satellite and the first communication satellite will be launched probably together around the end of 2028. So in this way, supporting the first establishment of navigation services, in particular for navigation, the one-way ranging service, and for communication establishing the first set of data relay service. And then in 2030, we have the FOC, the full operation capability, where data 3 navigation satellites will be launched, in this way enhancing so the services of PVT, the time dissemination service, and also supporting the dissemination of the Lunasar return message, because also Moonlight so aims to anyway disseminate through the navigation message the return link message supporting the Lunasar return link service. Then we have the step 3, so starting from 2035 onwards, represented by the next generation of the Moonlight LSMS system, with the main scope to cover the entire moon. So in this way, ensuring a global coverage of our natural satellite. Giving you some details about the Lunar Pathfinder. So the launch is planned around mid-2026. It is a PPP initiative, a public-private partnership between ESA and SSTL UK. So it is represented as a first commercial lunar communication relay service, so Moonlight Step 1. And also will be launched thanks to a carrier represented by Firefly Blue Ghost LSPS C3 mission. So the lifetime of this satellite is around 8 years, and this satellite will host a high sensitivity GNSS receiver on board. So this satellite will embark a laser reflector, so that it is given by NASA in order to support the orbit determination estimation. So, and in this way, having a full demonstration of GPS Galileo PNT on a lunar orbiting satellite. So, like Lugre, so we have the possibility to host this high sensitivity receiver, GPS and Galileo, to have a first fix of PNT thanks to the use of the Earth GNSS signals. So we will see an high gain antenna flight unit that it is built by MDA. And also using an X-band ranging, because also this satellite will have a TTLC transponder working X-band. We can have the possibility to calculate in very accurate way the orbit of this satellite thanks to the use of these 3 ranging techniques: Earth GNSS, laser retroreflector, and X-band ranging. Now, talking about Moonlight, the scope of this mission is to provide communication and navigation services that are fully interoperable with other communication and navigation services provided by the other 2 main international agencies, NASA and JAXA, to support the current and next generation of not only institutional mission, but also private exploration missions. When I'm saying interoperable, communication navigation services, I can tell you that we are working with NASA and JAXA in the context of LunaNet interoperability framework, where we are defining some fundamenta in order to establish this interoperability between these different constellations. And for example, we are defining together a common signal space ICD, and according to that, the navigation satellites of these three different constellations will broadcast the navigation signals fully compliant with this signal space ICD. We are working with the industry, so then we will see what is the consortium behind this project from an industry point of view, where we are working with them. So in order to establish a detailed signal space ICD, having full interoperability with these other constellations. Moonlight is also a public-private partnership with an European consortium that is led by Telespazio Italia. So in this contract, ESA is supporting the development of infrastructure. ESA is the chair of the system activities, and ESA will be the first anchor customer. So the contract was signed last year in October. So during the conference in Milan, the International Astronomic Conference 2024. So a dedicated constellation of satellites around the moon providing commercial lunar communication navigation services in two steps, IOC, FOC, that I told you before, is planned. And we have different services so that are under design, so with the industry, to be provided to these future lunar users. So audio video streaming, direct web service, other additional navigation services like post-processing PVT in order to in a way determine accurate products, so for families and satellite clock error corrections, also to anyway having a sort of reference also to plan in advance missions to explore the moon, and also the Lunasar retooling service. But also we have the possibility to provide very accurate PVT. So thanks to the paradigm of multi-sensor PVT, because as you know, we have only 4 navigation satellites. If you consider only 4 navigation satellites, your performance anyway is degraded, because so sometimes you have in visibility only 3 satellites instead of 4. But thanks to the paradigm of using other sensors supporting you some challenging phases, like for example landing, we have the possibility to have very accurate PVT.
The idea will be also, Cosimo, to
Yes.
put a reference.
Yeah.
Are you planning to put a reference station as well in the moon in order to make like RTK or differential GNSS, something like this? Or
Yes. There is another initiative that it is called Nova Moon, and I also prepare some slides showing you that. Yes, the scope is to anyway deploy a sort of reference stations, also to support anyway the SNS, also in this way also a program related to that. But so now, the main focus is to design this constellation, but after, so around 2031, when also Argonaut lander will be launched over the moon, this lander will host Nova Moon payload, and Nova Moon payload will be a sort of reference station supporting LSNS like differential GNSS, but also supporting the process of defining anyway the lunar geoid, and also supporting the realization of a lunar time over the moon. But we will see later.
Okay.
So
Very good.
at the end of this presentation, I have some slides showing you what is the roadmap also to support this part, also a sort of augmentation of the LSMS system.
Very good.
So this program is a multi-domain program. It is the first time in ESA where we have a multi-domain program. 3 different directorates are involved in this initiative: navigation department, also the connectivity and secure communications department, and also the human and robotic exploration. So
you can,
in this way,
Cosimo,
yes.
Can you hide maybe the banner that you have below? You can hide it, right? You can just push hide. No, I mean,
okay.
there is a button that is hide, and you can hide it directly. You know?
Okay.
Exactly, perfect.
Okay, it is the first time where we have 3 different departments, 3 different directorates involved in this initiative. We have navigation, so we have in this way the opportunity to have support from experts from the navigation department. So as you know, navigation department was the department that designed Galileo first generation. Now they are designing Galileo second generation, and also they are working on the OpenT initiative and Genesis. Then we have the connectivity and secure communication department. It is located in Harwell, and the human and robotic exploration directorate departments. So in this way, we have the possibility to leveraging expertise from across ESA, and also ensuring a strong cross-domain fertilization and capability.
There you go.
So some news about the contract signature, as I told you before, was signed between Telespazio and ESA during the International Astronomical Conference in Milan, so on the 15th October 2024. The consortium is led by Telespazio. Telespazio is the system integrated responsible of this initiative. For navigation activities, TASAI is the leader, while Viasat is the leader for the communication system activities. TASAI is responsible also for design of the navigation satellite and design of the navigation management center. It is the navigation mission segment of the EGS, the Earth Ground segment. NGV and Deimos are working with Thales in the development of the most important facilities of this navigation management center, like ODTS facility, the post-processing facility, the message generation facility, the external provider interface manager, and later we will see details about that. Then there is Ispasat working with Telespazio as a service provider, and Viasat also is involved as service provider together with Ispasat and Telespazio. And then, so for the communication satellite, the responsible is SSTL, and MPA is responsible for the communication payload, while Quasco is responsible for design and development of the navigation terminal user segment, together with Telespazio UK. Telespazio UK is working with Quascom on the definition of the multi-sensor algorithms and also the implementation of these algorithms in a dedicated FPGA. Also, in this consortium, there are many different universities, many different research centers, because it's important also to have support and expertise from scientists, because for the first time we are anyway designing a new concept. One of them is the ODTS, because ODTS is completely different from what it is defined in Galileo, and we will see later some slides about the ODTS concept baseline. Other news, so a PTP was also organized between Telespazio and ESA before the contract signature. So
different milestones were held. So having the final outcome of the baseline requirement review, the BRR, system BRR and segment BRR. And now we are working with the industry to set up the system PDR. So in the second week of June, we will have the co-location, so with the industry, for system PDR step 1, focusing on the navigation chain. Later, we will have the system PDR step 2, focusing on communication chain. And then in July, we have the co-locations for EGS PDR step 1, focusing on the part of EGS that are involved for the navigation chain. And end of July, we have the co-location for the LSS nav PDR and LUT nav PDR. So this is the main plan.
You will talk a little bit about the GS, the ground segment, the facilities, the sensor stations.
Yes, I have some slides about the GS architecture and also focusing on the part about the navigation management center, that it is the equivalent of the navigation mission segment, and also giving you some on sites on the main facility. So of this
like the OSPF, right? How to build the navigation message and so on, right? Yeah.
Yes. I will show you the main concept behind ODTS capability. So before joining ESA, I also worked with the colleagues from TASF and GenV on SPF in the context of Galileo system worker the one. So with ESA, and as you know, so the SPF is a very complex machine, and it is the crucial part of the navigation chain. So if the SPF is not well designed, so you have problems everywhere to provide navigation service. ODTS is the crucial part.
I was also involved in the USPF in Galileo for many years, and I was responsible for the algorithms of the ODTS in the MSF. You know the MSF, the Mission Support Facility, which is estimating the orbits. And I know the problematics very well, right?
You know very well the problematics. And what it is very difficult, I remember, is to anyway tune the barriers. The barriers inside SPF is very difficult to tune different thresholds. So because otherwise you have reset fault or some anyway false alarms. It's very difficult. I remember when we should tune these barriers, and also correlating the triggering of the barriers to the field events on board of satellite or on the mission segment.
We work a lot in EGNOS with the different barriers and triggering, the thresholds, and so it's very, very difficult because you have many different field events at the ground segment level and space segment level, and you have to handle all together. Yeah, but in fault free should be okay. In fault free shouldn't be a problem, right?
Yes. And then, closing this slide about another important initiative, mainly followed by Xavier Ventura, because Xavier Ventura is the father, as you know, of this initiative. So a Luna PNT working group was created during the last ICG, also to support the definition of a signal space ACT, but also some important topics like reference frames. I have some slides about reference frames showing you what is the status on definition on these reference frames for both selenodetic but also timing reference frames, because time on the moon is another important topic to be investigated and studied. And so in the industrial consortium, but also from our side, we have some important experts from Europe, also to understand what kind of reference frame we should use for selenodetic and also for timing aspects. We will see later some slides about that.
That's a big challenge.
And so on. It's a big challenge. I presented some slides during the last Luna PNT working group in Vienna in February, and there is a strong debate on which kind of timing reference frames we should use. So referred to the center moon or referred to the lunar surface, like an equivalent to UTC.
Exactly.
But so moon is another story, because the gravitational effects are different, because anyway you have a lot of secondary effects, for example the tidal effects, that can influence anyway the time on lunar surface. Probably you can have a very small difference of time on two different points on the lunar surface. And there is a strong debate about that, because so in order to have a more pragmatic approach, probably it would be better, following anyway a baseline where the time reference frame is defined with respect to the lunar surface, because in this way you have a strong analogy with Earth. So it is very easy also to relate to the UTC. While having a time reference frame with respect to the central moon, so probably you have an absolute anyway reference that cannot anyway depend on definition of the lunar solenoid, and not depending on which point of lunar surface you are. But we will see later some slides about that.
Very good.
Because so now, yes, the experts are working on it. We were having important meetings with them in order to understand which kind of reference frame we should use, and also to discuss with NASA and JAXA, because in a way we should adopt a common reference, because so reference frames are important aspects to be taken into account when you talk about interoperability. If you want anyway to make a seamless PVT using different signals coming from different satellites, anyway you should use the same reference frame, because anyway in the navigation message you should have the parameters to determine your position on PVT.
Exactly.
We will see.
Exactly.
See later. Yes, we will see it later.
Let's go. Go ahead. Yeah.
Go ahead. Okay. So high-level mission and service drivers. So what it is important, I told you before, is to anyway ensure interoperability according to the LunaNet standard, supporting all mission phases. Now the scope is to cover the south pole on the moon. What means south pole of the moon? In the area with the latitude between minus 70 degrees, minus 90 degrees on the moon surface, but also considering service volume 2 with an altitude of 200 kilometers above moon.
For the landing.
Yes, supporting not only the landing, but also supporting the orbiter.
The orbit too.
We should also support the orbiter, yes, too, because we have three different use cases. One is the orbiter, the second one is the lander, and the last one is the rover.
Exactly.
So we have defined at the SRT level different, anyway, accuracy performance required, and also different communication requirements for these three use cases. I would like to show you some details about the communication and mission overview. So my presentation is much oriented on navigation, but so I would like also to show you some details about the communication mission. So what is the coverage that is required? So it is required a service coverage that should be continuous with a value of around 8.5 hours in the service volume 1 South Pole and the service volume 2 South Pole. The service window per day should be 16 hours per day, and we should support users. So in South Pole 1, in South Pole SV1, SV2 South Pole, and multiple users in SV1 South Pole 1,000 kilometers. Some numbers about data rate, because we should support different proximity links in S-band and K-band. You see different values for the forward and return links. So surely, thanks to the K-band, we can support higher data rates, around 50 megabits per second. So for forward, and for return 100 bits per second. And also, we can support simultaneous users. So the scope is to support 2 users for IOC and 4 users for FOC. The communication satellite will be launched in 2028, probably with the first navigation satellite, and then for FOC phase, probably a software patch will be uploaded on the communication satellite. So in order to enable higher capabilities like this, supporting higher data rates and supporting also simultaneous users in terms of forward.
How many satellites do you have in the communication constellation?
For communication now, the scope is to launch only 1 communication satellite, a big satellite. We are talking about a mass of 1,000 kilograms. So it's a complex machine supporting the K-band and S-band proximity links and the trunk link in X-band and K-band. So, because as you know, we have a big constraint also in terms of the total cost of the infrastructure. And after many trade-offs that were carried out by industry, we agreed up to now, because communication satellite is under design, and anyway the communication part is slightly delayed. Up to now, I can say, so the scope now is to launch 1 big communication satellite, probably later. So
in which orbit? Always visible from the South Pole?
Yes. We will see later in which orbits, but the orbit is Earth orbit. So we are choosing elliptical lunar frozen orbit, because this kind of orbit allow to have a revisit time over the moon that it is almost over the South Pole of the moon, almost continuous.
That's
so
good.
After mission analysis, trade-offs and so on, the final orbits that we selected for both communication and navigation satellites are helpful. Surely they have different features, but so for both we have selected the orbits because these orbits are stable and they can allow to have a high revisit time, so almost continuous over the South Pole of the moon.
Amazing. Very good.
Yeah, this is a picture showing you the different links that the communication satellite will support. So the expanded TNC with the Earth stations and the trunk link in K-band, and also the proximity link forward and return real time and not real time in K-band and S-band with the different data rates, and also supporting user-to-user via relay. So this is another capability that this satellite will host. So now focusing on the main challenge that impacts the lunar satellite navigation infrastructure design, I can say we have many different topics, many points of attention. We anyway spent a lot of time on each of these topics. We are defining anyway the architecture of the system. But so I can say, so in the past we studied these topics in different activities, in different feasibility projects in order to define the best candidate for them. So first of all, the problem orbit, because for the first time we should solve the 3-body problem, because we have 3 anyway bodies, Earth, Moon, and Sun. with the main scope of covering the south pole of the moon and also optimizing the KPI navigation. What are the KPI navigation? It is the service coverage, the temporal and spatial coverage, and the top. So these parameters are so important when you anyway define the candidate orbits to provide the navigation services to potential lunar users. So another important topic is to define the reference frames, because so anyway the reference frames are fundamental in order to ensure so high accuracy navigation services. Another topic is the environment. So you should design solutions that are tolerant to radiation, and also it depends on duration of the navigation mission. I can say that for the navigation satellite, so the lifetime is set to 6.25 years, while for communication satellite, the lifetime is 8 years.
Okay.
Then another topic, so it is the ODTS. What is the candidate solution for ODTS? Orbit determination in time synchronization system concept. When I was in Thales Alenia Space, I was the technical manager of the lunar radio navigation system, where we studied the ODTS concept together with the ESA, and for the first time I studied the novel concept, so that may be conceived for exploration topics, and we will see later what is the concept behind that. In this assessment, I'd like to say that it is not so important only the accuracy that you can achieve, but also the readiness of technology. You should anyway understand what kind of technologies your companies have in-house to establish anyway a strong and mature ODTS concept, and also take into account the final cost of solution. So these aspects are so important when you define an ODTS system concept, because as you know, there are many different topics, many different solutions on the table, like interstellar link, like for example autonomous ODTS based on use on a space-based receiver on board of navigation satellite. Yes, it's true, but it is also important to take into account that you should anyway design a system where the first navigation satellite will be launched in the next anyway
3 years.
2 years and a half.
Yeah.
Yeah, because now we are mid 2025. The first satellite will be launched so at the end
2028. Yeah.
Yes, that 2028. Probably so the satellite will be ready before, but meantime we are discussing
the launch.
The launch. Yes, we are discussing with the launch providers. So it's important also to take into account that. Another topic, as you know very well, is the clock technology. Which kind of clock are using on board of the navigation satellite? It's important to say that we are using a platform for the navigation satellite that comes from the ERIDE program. So the platform is a Nimbus platform. So ERIDE is another program followed by Thales Alenia Space for another scope for Earth observation. The lifetime of the satellite is around 1.5 2 years. So this is another concept behind that. And in order to use this platform, a strong effort was carried out in order to improve the redundancy of the units of this platform in order to ensure a higher lifetime. It is important to host, anyway, a nice stability and compact clock on board, because otherwise we cannot embark on the navigation satellite PHM, for example, because PHM...
It's very heavy, it's very
yes, it's heavy, yes, and anyway, we should use a clock that it is a good compromise in terms of the accuracy performance, no, that is required in terms of signal space, signal error. We will see later. Then another important topic is to design the signal modulation techniques for the lunar environment, because anyway, you know that we have the problem of lunar craters and so on. So it's important also to define a robust modulation technique. And anyway, this robust modulation technique should be at the same time simple, because otherwise you have constraints on design of the receiver, because so the readiness also of the terminal is anyway an important constraint to be taken into account in design of the terminal. And so the signal space facility I mentioned before, ensuring interoperability and compatibility with NASA, JAXA, LunaNet initiatives. What is the mission architectural concept? So this slide showing you what is the main concept behind the mission. So we have an EGS on Earth. We have 3 different sites that are equally distributed over the Earth with a longitude of 120 degrees, in this way improving the visibility of the navigation satellite with respect to the Earth. So these sites are located, one in Scansano in Italy, another one in Australia, probably in Adelaide, and another one in Riverside in US. For this reason, to improve the visibility of the navigation satellites with respect to the Earth. What is the way to track the satellite? We are implementing a novel technique that it is called multiple spacecraft antenna aperture, or multiple spacecraft per antenna. So in each site, we have an antenna with a small diameter, lower than 1 meter, so able to see and track simultaneously the 4 navigation satellites with respect to the JSN station. JSN means ground station network that it is located in these 3 sites, and implementing in this way ranging and two-way time transfer using the TT&C link at X-band, implementing the CDMM technique in uplink and CDMA in downlink. Satellite is identified by a unique CDMA code, and in this way we are using on board of the navigation satellite an integrated deep space transponder. So this unit is a jewel of Thales Alenia Space, able to implement ranging a two-way time transfer with the Earth station. On ground, we have this antenna, MSPA, that it is connected to a ground modulator, so a baseband ground modulator able to implement this CDMM technique with the 4 navigation satellites, and also implementing ranging a two-way time transfer, because anyway is a two-way process. And in this way, we can achieve accuracy in terms of signal space, signal error, that is the main driver in design of the system, around 10 meters, considering an age of data of the navigation message of 2 hours at 95%. To this TT&C link, we have also the possibility to uplink the navigation message to the satellite, that satellite then broadcast to the user through the FS in S-band. FS means augmented forward signal. This is an acronym that was decided with the JAXA and NASA in the context of LunaNet interoperability context. So this signal is operating at S-band in the frequency interval between 2483.5 megahertz up to 500 megahertz. And so in this way, we have these 4 navigation satellites for FOC to able to broadcast the S-band signals to a potential lunar user. So the TNC is operating at X-band, so also an important trade-off was carried out in order to understand what kind of the frequency bands is the candidate. This band is a good compromise, also take into account the readiness of the technology. For the communication satellite, we have also the trunk link in K-band. So in each site, we have an MSPA antenna plus a redundant MSPA antenna supporting the nominal mode, supporting the navigation service provision. Then we have the K-band that it is used for the communication satellite, and also this antenna is used anyway, because this antenna is also able to support X-band because it is a big diameter antenna. We are talking about of 14 meter of antenna, supporting also the contingency of the navigation satellite when the navigation satellite is in safe mode. So, assuming we have in each site one antenna with the diameter lower than 1 meter supporting the MSPA technique, that is novel concept for navigation, plus a redundant antenna, so for redundancy reasons. Then we have a big diameter antenna of 14 meters supporting the TTNC link and trunk link with the communication satellite in K-band, X-band, and also using this antenna when one of the navigation satellite will be in safe mode. Okay?
Then
there are questions?
When you were talking about the signal in the space accuracy, you were meaning the orbit and the clock together, right?
And
delivered every 2 hours, right? Then you are targeting to have less than 10 meters, 95%. This is a requirement, right?
Yes, this is a requirement. We will see some details about orbits. Yes, I prepared a slide, slide on that. Yes, we have this number, 10 meter. So at 95% over any 24 hours. So in terms of signal space, signal error. And it is important to say that in each JSN station, we have also a time generation and synchronization facility. It is called TGSF, where we have a master clock in Scansano, responsible for the generation, of the system time that anyway it is steered to UTC thanks to a connection with UTC key labs. So we have a master station able to generate the SNS system time because we have an HM plus a GNSS timing receiver able to generate the LSNS system time that anyway it is linked to the GPS Galileo system time. And then we have data to stations that each station we have a secondary time generation synchronization station that it is based on use of another HM plus a GNSS time receiver. And these 3 stations are synchronized among them by all GNSS in view approach.
That's what I want to ask you. They are also synchronized with the constellations in the Earth, right? GNSS. Galileo, you mean, and GPS on...
Galileo and GPS, yes, Galileo and GPS. And so in this TTNC link, also you are synchronizing the time of the satellite together with the time on ground, thanks to a two-way time transfer algorithm. So this is the concept behind the timing synchronization.
Then at the end, the approach to, let's say, to deliver, to steer the time, the system time is pretty much the same as the one in Galileo with the PTF, right? You have a PTF, the master clock, so where you have the active hydrogen master clocks and maybe some cesium clocks, yes, more or less.
Yes, the approach on ground is the same, is equivalent to Galileo first generation, because anyway, in each JSN you have an HM plus a GNSS time receiver, and these 3 stations are synchronized by all GNSS in view. This is heritage from Galileo. The novel technique is behind the concept of MSPA, because they are using a small antenna on ground able to track these 4 navigation satellites, establishing ranging a two-way time transfer with this station when the navigation satellites are in visibility on this station, thanks to the TT&C link. So this TT&C link is able to support not only the provision of telecommands and also sending telemetries from satellite to ground, but also the process of ranging a two-way time transfer together in the coherent mode.
It's like you have let's say you have like the TTCs of the ground control segment and the GSS together, let's say, right now. Yes?
Yes,
Yeah.
yes.
And
because anyway, we cannot deploy up to now any infrastructure on the moon. We can exploit what we can deploy
in the Earth.
On the Earth. Yes.
And what about the master control? I mean, the CP, or let's say the OSPF, where will be?
The OSPF will be located anyway, because we are using an approach based on virtual
cloud,
virtual navigation management server, yes, like on a cloud. And so anyway, in Scansano, this is the main facility. We have anyway the cloud where all distances of the different modules of the navigation management center will run. But OSPF design and also development is under responsibility of TASAI together with JNV, because JNV is the sub of TASAI developing this facility. Yes.
Yeah, the last week we had Miguel Romay from GMV, right? He was talking about they were involved in the architecture of the ground segment for the lunar navigation system as well, the equivalent OSPF.
Yes. The equivalent, yes. GMV is very active on that, and I remember when I was at Thales Alenia Space, I had several meetings with them to explain the concept that we want to implement, and also asking them that, because these people are very expert, as you know, on implementation from algorithm point of view. What are the main challenges that we are expecting in design of this facility? What are the main differences with respect to the Galileo SPF? First of all, the system is single frequency. We are using X-band, so we are using the TT&C link also to upload on satellite navigation message, but the navigation message is broadcasted to the user at S-band. We should know what is the bias between the X-band data and S-band data. There are several topics that anyway require involving big expert.
Then you mentioned that you have only monofrequency signals, right? No bifrequency, monofrequency. Yes. Then what about the ionosphere when you are approaching the Earth? Let's say, what happened? Do you have any problem with this?
Yes, we are discussing with the industry to address that, because anyway, ionosphere is an important anyway aspect to be taken into account. They are saying me that they want to use potential tech maps from IGS to anyway understand what is the residual error to the ionosphere, especially when you are anyway in uplink, because at the moon you don't have atmosphere, so this problem is absent because you don't have troposphere and ionosphere. Yes, but for
the OSPF, let's say for the processing of the orbits, let's say there's a problem. You have to mitigate, correct somehow, right?
To mitigate, correct, and so on. They are anyway studying this problem, and we will see also during the segment PDR, so specifically on the DTS facility that it is planned around end of July. Yes, but there are many topics on the table, potentially open issues that we should solve, because our system anyway is a single frequency, because as you know we are for the first time designing an infrastructure so that should be ready as soon as possible. And we are trying to minimize anyway the degrees of freedom in design of the system. Yes.
In order to speed up the development process, right?
Yes, in order to speed up the development process.
And then you're using as well code measurements and phase measurements on ambiguity resolution, or this is not yet, let's say, fixed.
Yes. The anyway, the satellite is also to acquire carrier phase measurements, and also carrier phase measurements will be available potentially to anyway support the processing in order to acquire very accurate data. Yes, this transponder is able to support not only code and Doppler measurements, but also carrier phase. Yes, Eduardo. Yeah.
Very good. Amazing.
Okay, I would like to show you this slide because before we talked about lunar orbits. So lunar orbits, so the candidate baseline are the alpha orbits. We are talking orbit, we characterize it a very high eccentricity. So the propagation period is 24 hours. So the main requirement behind the final selection of this orbit baseline is to ensure a minimum 15 hours of continuous PNT service over South Pole, considering any 24 hours. So we optimized the value of HH-DOP. What means HH-DOP? Means that the DOP, in this case, is 8 constrained. So we are assuming that the vertical component is estimated using additional sensors like altimeter, like digital elevation model. In this way, we can have an HH-DOP lower than 3.5, because considering only 4 navigation satellites, it's very difficult having an H-DOP very low. And we introduced this artifact because anyway, the PNT service with very high accuracy numbers is established also using other sensors. So having a sort of PVT engine that is multi-sensor, able to combine measurements also from other sensors, because anyway, lunar users are equipped also with other sensors, at least IMU, altimeter in case of lander. In the case of the orbiter, you should have an orbital filter in order to speed up the process of the convergence of the Kalman filter, so the PVT solution. And also in the case of the rover, you should have at least a digital elevation model and an IMU. So this is a new paradigm with respect to Galileo, because Galileo in the baseline, originally you have 24 satellites, then so you have Dadar 3 and Dadar 3, so 30 satellites. In our case, we have only 4 navigation satellites, and anyway, in order to achieve a very accurate performance, you should introduce this new paradigm. What are the services that will be provided? We are talking about one-way ranging, so as initial performance anyway, when we have only the first navigation satellite, PVT, not provided surely for IOC, but full performance for FOC, the time dissemination service, so it is planned for FOC, two-way measurement. This service is new service that it is not established by the navigation satellite, but it is ensured by the communication satellite.
Which one you say?
Yes, the two-way measurement. Two-way measurement service is a two-way ranging service that it is established by the communication satellite, able to talk with the communication terminal asking this service. But anyway, it is a service that it is classified within the navigation services, because anyway, if you have the possibility to have a two-way measurement, you can combine this two-way measurement with other satellites, the other communication satellites belonging to the other constellations, because NASA also is deploying communications. Also, JAXA is anyway developing a communication satellite. And if you are able to have two-way measurements with other constellations, you have anyway an additional navigation service. For this reason, it is classified within the umbrella of the navigation service. Two-way measurement is established by a two-way link between the communication satellite and the user terminal, asking to start the ranging session with the communication satellite.
Okay, it's a kind of RTK, let's say, service that you can ask to have additional information to enhance, let's say, your navigation thanks to the two-way measurement from the communication satellite. That's
is like for aeronautical domain, like an equivalent DMA, distance measuring equipment, is much similar to this aeronautical radio navigation service, no?
Yes.
But it is another capability that our system is able to provide anyway to cover the gaps that we have only 4 satellites for navigation, only 1 for communication.
Very good.
Okay. Is an animation. The performance that are required at service level. So we have, as I told you before, 3 different use cases. We have the surface rover, where the accuracy that is required in real time should be lower than 10 meters at 95%. In post-processing, 3 meters at 95%. Then we have the lunar lander. So we are asking an accuracy in 2D, because anyway, for the vertical component, we should use in the landing phase an altimeter. We are asking 50 meters at 95%. And for lunar orbiter, we have an accuracy in 3D lower than 100 meters at 95%. So in this case, in the case of lunar orbit, we are also assuming to use an orbital filter to speed up the convergence of the solution. So, an orbital filter, yes. It is planned also in the case of lunar orbiter having an orbital filter. So below you see some simulations results so that were published in different conferences from my colleagues at European Navigation Conference and Navigation Journal, and during the Young GNSS 2023. I already explained the concept behind ODTS, so based on direct Earth tracking. It is a novel technique that in the past was studied by NASA for Mars exploration. And I remember when I was in Thales Alenia Space for the first time, I studied this technique because there was a parallel contract led by a research center of the University of La Sapienza, led by a very famous professor, so usually works with NASA and JPL, and also working with my previous colleague from Thales Alenia Space, responsible for the design development of the TT&C transponder. This transponder was also embarked on Baby Colombo, was embarked on JUICE, was embarked on other interplanetary missions, and we discovered that so the company is this dual able to support ranging and also two-way time transfer. So for this reason, we decided anyway, in order to speed up the process of development of the infrastructure, to use this kind of technique, because as you know well, if you want to use autonomous ODTS, anyway, a spaceboard receiver on board of a navigation satellite cannot achieve these numbers, because
it's too far away. It's too far away.
Yes, it's far, and also the DOP is very is very, very bad. And anyway, you can also potentially track the Earth signals.
You just
can
can
estimate the PDT. Okay.
Can you just
Yeah.
confirm that when you are estimating the ODTS solution for these 4 satellites, you are using also a combined solution using GPS and Galileo together, right? Otherwise, wouldn't be possible, right? Or you are using only these 4 satellites in the ODTS solution with these 3 stations?
No. In our solution, we are using only the LSNS measurements. We are not using the GNSS measurements because on the board of satellite we don't have any GPS receiver, the Galileo receiver, plus an antenna.
No.
An antenna.
What I mean is in the ground stations that you have on Earth,
Yeah.
right? Are they tracking as well the GPS and Galileo constellations or not?
No, we are not up to now. So the only thing is to anyway having a GNSS timing receiver only for timing aspects in order to establish the system time that it is linked to GPS and Galileo system time. But if you are asking me, so in the DTS process, if we are using also GPS and Galileo measurements, it is not planned up to now.
No, because you know when
it is not,
you know when we are in Galileo in the phase IOV, you know in the beginning we have only 4 satellites Galileo. We had to combine with the GPS satellites in order to have, let's say, a precise orbit determination. No, as long as we were deploying more and more Galileo satellites, we can remove the GPS satellite. Right? In this case, I think maybe a combined solution, multi-constellation, could be better for the estimation of the orbits of the 4 navigation satellites in the moon, right? I don't know.
Yes, yeah, but about that, in our architecture, we have some monitoring stations on the Earth because now in this slide we are anyway seeing that. So we have these 3 stations, but maybe are TTNC station. But in our architecture, we have some monitoring stations because anyway the signals that are transmitted by the LSS nav on the moon surface on South Pole anyway are so we made some analysis also taking into account the visibility on each side. We have also the possibility to receive these signals on Earth using a big antenna and working on side lobe of this antenna. In our architecture also, we are planning to have some S-band monitoring stations over the Earth, also to receive the S-band signals on ground using the side lobe of this antenna. So some linked budget, some analysis were carried out in order to use these signals also to anyway monitor the infrastructure. And I can say that on board of navigation satellite, we have also a laser retroreflector. Laser retroreflector will be also used to enhance the orbit determination process.
Okay. That's good. Okay.
But in our architecture, so we discussed a lot with industry if we can also put a receiver on board. The problem is that is to accommodate additional units on board the navigation satellite because the satellite is based on small platform. So we are talking a mass around with margins 400 kilograms. And so the satellite is built according to some trays, and in each tray, so the units of payload and other subsystem of the platform are allocated. So, and if you want to put another antenna, because you should put a steering antenna on satellite pointing Earth, I don't know. So if we can have enough space also to host that. On board the navigation satellite, in order to close the link with the small antenna on ground, we have also an MGA. So the TTNC link is established by a small antenna on ground, and on satellite we have an MGA antenna. We are talking in a steering antenna of a diameter of 35 centimeters. And this antenna is able to steer and pointing towards the Earth in order to establish the TTNC link in the nominal mode.
Okay.
Okay.
Mm-hmm.
I don't know if there are some other questions on this aspect.
Do you have any questions, guys, on this? Is it clear? The global architecture, it's not easy, right? I have to understand everything, right?
It is not easy. There are a lot of concepts behind, yeah.
But I guess they are concepts that they already know more, because we have already, talked about Galileo, SPF clocks, and these kind of things. The main global concepts are more or less the same. The global concepts.
Yes, the global concept is the same, because anyway, in order to speed up the process of development of this infrastructure, we should start from well-known concept, because otherwise, if you want, I don't know, study solutions based on SL, based on autonomous ODTS, yes, you can make it probably for the future generation of the system. But up to now, as you know, these technologies are under study and design for the second generation Galileo. It's not the reality on Galileo first generation.
Yes.
And for this reason, we should rely on what it is available. And also, thanks to a previous feasibility study, we made a lot of simulations. We also developed an ODTS simulator, able to implement this range and get weight between Earth and satellite, in order also to demonstrate that the CISA is compliant with number, and also defining in details the OD and TS error budget.
Yes.
So also verifying what is the impact of the solar radiation pressure on the ODTS process. Also verifying what is the impact of other additional secondary effects on the process of the estimation of the orbits and the clock error correction.
Relativistic effects are a lot, right, as well, right?
Yes, relativistic effects. And also for the first time, we are hosting on board a technology, mini-RAFs, that never flies before, because, as you know, this is a well-compact technology based on strong use of RAFs technology. RAFs clock is on board of Galileo first generation, but anyway, for the first time, we are assuming to use this technology, because this technology is a good compromise in terms of accommodation on board, in terms of potential impact on the performance due to thermal effects, to vibration effects, and also taking into account the performance that are required, because we are asking 10 meters of error, so combining orbit and timing parts. Okay, some numbers, some simulations, so that I would like to show you. So considering some assumptions that we made on the wet troposphere calibration, ionospheric calibration, the timestamp, empirical acceleration, and so on. And also assuming a modeled antenna niche area, because I said you before that we are using an MAGA on board. And you see that, so considering three different conditions, mainly focusing on the phase 3, it is represented by GNSS dual frequency data. So in the process for the ionosphere, we are assuming also to use GNSS data to try to estimate what is the ionospheric impact. Surely L-band should be also translated to X-band, because our TTNC link works at X-band. In X-band for TTNC, in S-band, the navigation signals are transmitted to the user, and also using advanced models regarding the wet troposphere calibration. We see that we have, considering mini-RAFs at 95%, combining both orbit delineation and time synchronization aspects, that the CISA of 10 meters is established around an edge of data of navigation message of 2 hours. So what it is important to say that in the DS process, as Eduardo said before, is also important to define in details the error budget, how you can calibrate and model the errors, because they have an important impact on the overall ODTS process, because the ODTS algorithm is mainly the same on Galileo, so it is based on classical algorithm for orbit determination, time synchronization, processing. It is not new in terms of algorithm, but what it is important is to calibrate the errors, calibrate the different models. For this reason, we are also mounting on board a satellite laser reflector also to support this process and also to generate a reference, at least for orbit determination, in order to obtain these numbers in terms of signal space, signal error.
Mm-hmm.
The navigation space segment overview, we already said that, so the space segment includes 4 navigation satellites. The lunar user segment also is the main scope to develop terminals for the on-ground validation, and also developing engineering models and flight models for future LSNS navigation user terminals. But the main scope in framework of Moonlight is to design terminals to support the on-ground validation of the system, because in the future other initiatives will be launched by ESA in order to design and develop in details terminals for these 3 use cases, lunar terminals, but in our case the terminals under design development in Moonlight are representative of the lunar terminals, but they are used on ground for validation of the system. So regarding the deployment strategy, we have say that, so for the first launch, probably the navigation and communication satellite will be launched together. So for the navigation satellite, I said before that it is based on TASAI Nimbus platform, new Italian microbus platform. For the phase full operational capability in 2030, we are launching other 3 navigation satellite in order to have a first constellation covering the south pole of the moon. So some details about payload. So the clocks are mini rafts that are hosted in dedicated tray. The navigation signals to the end user is through S-band using a phased array antenna, and we have a laser ranging reflector to measure the satellite position from an Earth satellite laser ranging network. EGS physical architecture. Before we talked about the ground station, Site 1, Site 2, Site 3. Then we have so the core of EGS, that it is composed by the navigation management center for the navigation chain. Inside, so we have the different CIs needed to establish so the navigation service provision. Then we have the mission operation center that is common to every satellite mission to support the operations. The communication management center, it is equivalent to the navigation management center for communications. And then we have the service management center. It is the center able to provide an interface towards users, institutional and commercial users. Then we have externally to many different external entities able to talk to EGS in order to provide I don't know, reference frames products to provide a timing reference frame, to provide anyway the LUNASAR return message to be encapsulated in navigation message to be broadcasted towards the user. And so the satellite laser ranging network. So a lot of different external entities able to support our infrastructure. Like, for example, the ground station as a service, no? Because if needed, in order to support, for example, the contingency of the navigation satellites, if we have multiple satellites in this situation, probably we should use ground station as a service with a big diameter able to support the recovery of satellite when satellite is in safe mode. So DGS is another complex system.
Okay.
Yeah.
Very good.
It's another complex system, yeah. But anyway, we are trying to reuse strong expertise for each of these subsystems, thanks to the involvement of the companies, so in Europe, that have a strong background on that. EGS, the Navigation Management Center. So as you know, the scope of this center is to generate the navigation message to be uplinked to the navigation satellite, and also to generate the post-processed navigation products, in particular high accuracy orbits and high accuracy satellite error corrections. So anyway, to support the provision of the post-processing service when it is required by an external user. So the functional decomposition, as you know, we have anyway the main functions of a typical navigation mission segment, like the navigation product archiving, so the navigation data catalog and browsing, to estimate the DTS parameters, generate the navigation message data for the MGF, to format so the navigation message, and to uplink to the satellite will broadcast to the user. And then we have other functions like performance monitoring and prediction, also estimate the CISA. We have inside the EGS Navigation Management Center also the capability to perform two-way message generation, and so on. We have many different anyway functions that are needed to establish the EGS Navigation Management Center infrastructure. So you have the list of different facilities, no?
You have also, I've seen something about the authentic navigation message. Are you planning to put also some authentication in the signals?
Yes, Eduardo.
Very good.
Yes. At the SID level, we have also planning the authentication of the navigation message,
which is the but not at GSM level, at GS level, yeah.
Yes, at GS level. Yes, the navigation message authentication is performed on ground, so in our architecture, not on board. In order to simplify the process way, in order anyway to provide a fast provision of this service. Yes, we have, and it is realized through the message authentication and key management facility. Then we have the orbit determination time synchronization facility, as you know, so responsible for the generation of the navigation products and also determine the signal spacing error.
Mm-hmm.
The PVT processing facility, responsible to generate the high accuracy orbits and the satellite error correction products. So the architecture in this case is based on ODTS, but not working in real time. So we discussed a lot with the industry how we can implement this facility in order to have a sort of a reference with respect to real-time ODTS facility. Probably the idea is to use much data and longer arcs to improve the accuracy of the products. But so about this aspect, we are talking with the industry
maybe to calibrate as well the CISA, maybe, right? The CISA you can calibrate with the...
Yes, to calibrate also the CISA. Yes, surely. Also to generate anyway high accuracy products to support the planning of the missions, because so the missions, as you know, are planned in advance, and probably we can have a sort of a reference scenario, and also we can have a sort of prediction of the navigation performance that you can have in this particular condition, also considering that so the constellation is based on 24 hours orbits, and so you can also use all this information to plan in advance the mission in order to understand what kind of performance anyway you can achieve in this particular scenario. Then we have the navigation payload operational controller facility responsible for the anyway management of navigation payload and also to monitor the status of the health of the payload. And then, as I told you before, the two-way navigation facility able to generate the products for two-way service, CIS, MIS, service availability, and also to determine the orbit of the LSSCOM satellite, because this service is established through the communication satellite, and also EPI, so the external provider interface manager, able to receive and manage message from external entities like LUNASAR, because there will be a LUNASAR external entity, external authority, able to anyway talk with our architecture to the EPIM, and also to provide the SAR message to be formatted in the navigation message and then uplinked to satellite and then broadcasted to the user. For NavLoot, we have some numbers. We discussed it before. So for rover, potential sensors are IMU, digital elevation model. For lander, IMU altimeter. For the orbiter, so you can have an orbital filter. And as you can see, you have some reference for the user terminal swap in terms of size, weight, power, size and weight for antenna and for the receiver. So we have these numbers also coming from exploration department, that so in order to accommodate and use these terminals probably on a lander, you should respect some envelope in terms of mass and in terms of power, some reference numbers that so industry can take into account when they design the navigation terminal. And so, as you can see, so you have in this picture some simulation results, showing you what is the number that up to now we have achieved, thanks to the integration also of the LSNS measurements with other sensors. And it is important also, anyway, knowing what kind of performance you can achieve using only LSNS, and what kind of performance you can achieve if you have anyway aided by an external sensors. For our point of view, it's important to know what kind of performance we can achieve using only LSNS. But anyway, in design of our system, the main driver is the signal space signal error, because this number is impacting in the ODTS system concept baseline definition, because you don't have any atmosphere over the moon, you don't have contribution from ionosphere and troposphere, and URE mainly is driven by CISE, orbit determination and time synchronization error, and then you have the local effects, probably due to multipath, no? If you want to estimate the overall value of URE, because you don't have any other contributions, because you don't have atmosphere, for example, no? So CISE is very important when you design your infrastructure.
Someone have already investigated the multipath effect depending on where you are in the surface, or there are some studies on this?
Yes, Eduardo, we are starting on investigating this aspect, because we tried also to ask so if NASA has already some materials, but according to the Apollo missions, but anyway they have only data about potential definition of the multipath model, only from Apollo for communication aspects. But I can say you regarding the multipath for navigation signals, up to now we don't have any important
studies
material. So yes, because first of all we should understand also what is the impact of regolith, no? And also how the lunar craters can impact anyway the dissemination to the users of the lunar signals. But there are aspects that anyway require a big effort, and surely we can address these aspects in dedicated feasibility projects, probably involving research centers and universities on these topics. I would like to spend some words about the LunaNet interoperability specifications. We are working on NASA and JAXA to define interoperability standards for both, not only for navigation, but also for communication. The first consolidated version of the Signal Space ICT, it is called LSIS, the LunaNet Signal Space recommended standard for the FS, augmented forward signal. This is the navigation signal. Was published on February 2025, while the version 5, the final version 5, was published together in February. Now we are working on update of this version, the version 6. In the meantime, we are consolidating the TPC, so the remaining TPC and some TBD that we have in the current version of LSIS. Also, asking to the industry the final confirmation in implementation on that. Sorry, guys.
No worries.
It's a time when my children are walking.
Are hungry.
In my house. Oh, yeah, yes. Then we have a general picture about the PNT services. We have LANS. LANS means the broadcast navigation signal. FS, it is the name of the navigation signal. Then we have the point-to-point direct links, so that are mainly PNT or non-PNT, and they are implemented by potential communication satellites. And then we have supplemental navigation services. What means? For example, dissemination of lunar maps, dissemination of conjunction data. So some additional supplemental navigation services that can be anyway used to also enable safe navigation. For example, dissemination time, reference frame, orientation parameters, all this information are needed to anyway ensure a high accuracy navigation service. Some details about the
modulation,
augmented forward signal, yes, forward signal modulation. The modulation that we are selecting are based on BFSK. So we have a signal FS that it is modulated in phase and quadrature. So we have the data on in phase component that is modulated by a BFSK1, and also considering a primary code, a wave code. So with the characteristics that you see, so and also supporting a data rate of 500 bits per second. And then we have the Q component, the quadrature component on FS that is modulated by PSK5, and it is also modulated by a tier code, so based on 3 codes: a primary code, secondary code, and tertiary code. So this comes from a lot of analysis able to understand what kind of modulation, what kind of codes are the baseline. Some details about navigation message. Navigation message is composed of data frames. Each data frame contains 4 subframes. The subframe 1 contains the time of interval and the frame identifier, and it is characterized by a fixed structure. Then we have the subframe 2 that is transmitted every time. In each subframe contains the required information about the orbits, the clock error corrections, and also the alpha status of the satellites. Then we have subframe 3 and 4 that are transmitted periodically, maybe not in each frame, contains other additional informations, like, for example, almanac, like, for example, information about the time and the reference frame parameters conversions, or potentially also including augmentation data information. So the SB2, SB3, and SB4 are encoded using LDPC codes. So you see, so the location for the LNS message to the different subframes. No, we have 32 message, and so for each of these message, you have the location on each subframe is including it, and if so, this information is transmitted periodically or ad hoc, so when it is needed. So and if this message is planned considering the version 1.0 or not, because so in our system we are designing the navigation message according to the version 1.0, because as you know, we are speed upping the process of developing of the infrastructure, and anyway, for us, the reference is represented by the version 1.0. For example, augmentation differential corrections are optional, so probably are included in subframe 3 and subframe 4, and so are planned to be anyway included in these subframes now as empty packets, but surely when, so before we talked about NOAA Moon, when also this infrastructure will be available, also we have the possibility to send differential corrections to the FS.
Mm-hmm.
So this slide so is about the frequency plan. So what is important to say, we also should interact with the NASA and JAXA, and also the I2 organizations and SPGC organizations to anyway define the frequency plan for the different services, communication and navigation, and that's also is important anyway to work with them in order to have a clear picture of the frequency plan to be established. Some details about the reference frames. As you know, Earth is the reference, but is important also
to define,
speed up the process and also define reference frames can be adopted in short term. So the reference frames that are candidate for the selenoidetic frames are the principal axis and mean Earth. For long term, surely we can also think about an international lunar reference frames, like so with this name ILRF. But so it's important anyway to start from what is already agreed by the international community. And for our system, the reference will be the principal axis, because it is defined by the principal axis of the lunar tensor of inertia with the constant tide contributions. And this is the primary realization, because in relation to the lunar celestial reference system, so if you want to realize this body fixed reference system, you need only three angles: the precession angle, the nutation angle, and the rotation angle, and you can anyway generate the reference. The mean Earth reference system was in the past used for the lunar cartography. The origin of this reference system is in the moon center of mass, but anyway it is generated by a principal axis. It is a secondary realization starting from principal axis. For this reason, the scope from our point of view, and also agreed with the other agencies, is to use the principal axis instead of the ME in a short term for the PNT scope. First of all, because ME is derived from PA, and also the principal axis is applied also to the other celestial bodies. Yeah, and in the world there are two observatories responsible for the generation of the lunar ephemeris, considering different formats: DE from JPL and IMPOP from the Observatory of Paris. And we are discussing with NASA and JAXA what kind of format we can adopt, DE or IMPOP. Surely we are supporting, Europe, and so we want to propose IMPOP, while Americans are pushing on the Moon. So is another complex topic. Probably we should plan another talk, yes, on this topic. But up to now, the reference is what it is implemented on Earth, because you have the terrestrial time, that it is a coordinate time, and then we have the physical realization in green, that it is represented the TAI and UTC. UTC, it is linked anyway to TI and GNSS system time. Up to now, we have only TCL, the lunar coordinate time, so that it is defined by the international expert, but we don't have any equivalent to UTC. So for this reason, we are discussing anyway what kind of reference time in terms of realization we want to adopt. And up to now, there are two options. Option one, so the LRT is a lunar reference time with respect to the lunar selenoid or geoid. So Americans, they push more using the term geoid, yes, while the Europeans selenoid. But so in analogy with UTC, and so the option one is mainly pushed by by NASA. And option 2 is the lunar reference time scale at the Moon Center. So, because I explained you before, probably, so the gravitational effects are different, the tidal effects are different, and there is no a strict analogy with Earth case. But anyway, what we proposed during the Lunar 20 event in Vienna is to have the support of international time community, first of all, to define better the terminology, because as you see in this slide, there are a lot of terms that anyway should be defined. If it's important to define a sort of lunar time, is a coordinate time in equivalent to TT, and then deriving from that the physical realization of LRT, or we want to go directly of LRT. So it's important to anyway define terminology and the standard for the lunar reference time. And we're working with NASA and JAXA and with experts on trying to close this trade-off and adopting the final baseline. What it is important? It's important, first of all, to ensure interoperability, to be traced to the UTC, also for a long term, considering possibility to have a physical realization on the moon. So what we can have since the beginning, surely a paper clock based on mathematical model, so trying to anyway trace the lunar time to UTC plus a periodical drift, that it is a periodical component of the frequency shift, that it is due to difference of the gravity potential velocity between Earth and Moon, and in the future having a timing generated by clocks in the lunar environment. Nova Moon mission. So this is another initiative that it is supported by ESA, not in the directly in the framework of the Moonlight, but it is another different initiative, but so strictly related anyway to the lunar. The scope of the mission is to provide the first local differential cybernetic timing station over the world to enhance anyway the Moonlight navigation services and to support the scientific experimentation. So the scopes is to have a differential station, to have a timing reference lab anyway, hosting some clocks, probably mini RAFs on board of this payload, and a geodetic reference station based on use of 3 different ranging stations through TT&C receiver, implementing ranging from the Nova Moon payload from F, laser retroreflector, VLAPI, and also a LSNS receiver. And Nova Moon will be mounted as a payload on the Argonaut lander, and so it is planned to be launched around 2031. So when Argonaut will be ready. I told you, so implementing these differential techniques supporting the process of high accuracy orbit determination. So this is an example, no? Also, if you want to use codes or you want to use also phase corrections, surely if you use Moonlight plus Nova Moon at lunar South Pole, and also in the case of you are using also phase corrections, you can have very high accuracy PVT. It's important to say Nova Moon can anyway enable very high accuracy performance of the Moonlight infrastructure. But so the scope now is to, first of all, launching satellites around the moon, tuning all the problems, and then so in 2031, when Nova Moon will be ready, we can also having a first augmentation of the LSNS signals. So this is a slide showing you some details about Argonaut, because Argonaut also can have other payloads on board. A Argonaut probably can operate for a minimum of 2 years, but so the target is 5 years, including lunar nights, because surviving the lunar night is very complex thing. And also the scope is to launch Argonaut recurring missions every 2 years, including, so anyway, recurrent Nova Moon payloads. A slide about this interoperability demo mission with NASA and JAXA. I told you before, we launched the first satellite 2028. JAXA will launch their satellite. NASA, the system is called the Lunar Communication Radio Navigation System. We launch other 2 satellites. In this way, we have 4 satellites, and also thanks to the Lupex lander from JAXA, we can host some LSNS receivers and laser radio reflector, probably also mini RAPs on board of this Lupex lander. And for the first time, we can have the possibility to have some tests of interoperability between these different constellations. And we are working now with NASA and JAXA also to understand what kind of performance we can achieve based on simulations, and also take into account that satellites will be placed on different orbits, different orbital planes. So because they are anyway designing their system independently from us, and we should understand, putting the satellites together, what kind of performance we can achieve in terms of accuracy in a seamless way. So some details about the development plan. So now we have finishing the phase 1 at the end of this year. So with the scope is to anyway design infrastructure. Now we have different PDR system and segments, and so the scope is to close the phase 1, starting the CDR. Then in phase 2, we should anyway develop and realize the satellites, the common satellite terminal to be used for service validation, and also to have the ground segment tested and implemented. In phase 3, launching the Data 3 navigation satellites, and also implementing and testing the full capabilities on each site, supporting concurrently navigation and communication services with enhanced capabilities planned for FOC. So some slides, they are like very nice pictures about the future. So we have landers on the moon, we have orbiters around the moon. In the future, so the scope is to have a sort of a moon village over South Pole of the moon, because so the scope is anyway is to have a permanent settlement there, anyway to support the other future interplanetary explorations. And so it's not a dream, guys. It could be a reality in a very short term, because there is now a sort of Cold War again, but this time for the lunar race, because Europe, India, US, Russia, China, and also South Korea. Last time during the Young Conference, there is also a speech from South Korea. So there is a strong interest now going again to the moon, but this time, so anyway, realizing building a stable, permanent settlement there for lunar exploration, not only for water, not only for the exploration of the other planets, that it is much easier from South Pole of the moon, but also because there are a lot of resources. There are also metal, mineral, probably on the moon. And there is again a new strong interest after almost more than 50 years to go again on the moon. And surely this is a first step anyway to develop technologies for a future solar system while communication navigation. It's not a dream. I have colleagues working on this topic because the scope in the future is to define concept, also thanks to our expertise and knowledge from previous experience to start anyway building a mindset for developing a solar system, communication and navigation.
Amazing. Amazing. Thank you so much, Cosimo.
I have a small video of 3 minutes.
Go ahead.
Is an official video, and then we can close our talk. Yeah.
Perfect.
I would like to show you this video that was procured by the external communications from ESA.
We cannot hear it, but anyway, our... Yeah, no volume.
Going to the moon was the first step. Staying there is our next ambition. With dozens of international public and private missions setting their sights on the lunar surface in the coming years. But the technologies we take for granted here on Earth, satellite navigation systems like Galileo or GPS, video calls, or even fast file transfer, are very limited on the moon. Since the Apollo program, very few lunar missions have managed to land successfully. We cannot have a sustainable lunar presence without reliable and autonomous communications and navigation. That's why ESA is working with its industrial partners on the Moonlight initiative to become the first off-planet commercial telecoms and satellite navigation provider. Launched into space, 3 or 4 satellites are carried into the moon's orbit by a space tug and deployed one by one to form a constellation of lunar satellites. These relays connect to Earth via 3 dedicated ground stations, forging a data network that spans up to 400,000 kilometers. The constellation's orbits are optimized to give coverage to the lunar South Pole, whose sustained sunlight and polar ice make it the focus of upcoming missions. Moonlight will provide data capacities sufficient to serve these planned and future missions over the coming decades, with a navigation service that enables accurate, real-time positioning for all lunar missions. This is the Argonaut. This, or any lunar lander, could greatly benefit from the Moonlight program. With a simplified navigational subsystem, our lander saves mass, reducing cost and enabling other equipment to be carried. Its position is tracked in orbit and descent with accuracy of just a few meters.
Perfect. You can maybe unshare the screen, Cosimo. Go ahead.
Sorry. No, that's the video is finished. Yeah.
Yeah, you can unshare the screen maybe, and you can see everybody here.
Okay.
Yes.
Okay.
Wow, that's fiction, right? Thank you so much for sharing all the plans that ESA and everybody has on the moon and the future solar system. Who'd like to work with Cosimo in ESA on this project? Cosimo, you can recruit here people.
Yes. I'm so happy to recruit people. Very, very good scientists and navigation experts. Yeah, because Moonlight is a very big challenge. As you said before, there are a lot of technical topics to be faced, a lot of open issues to be addressed, and we should have support from experts. Europe, because it is the European project. Now, maybe supported by Italy and UK, with a small contribution from Spain, a very, very small contribution from Portugal. So there are other nations like Switzerland, Norway, but so very small contributions. But in the future, for the phase 2 and phase 3 for the ministerial 2025, 2028. So it's important to have support from Spain, strong support from Portugal, but also from France and Germany, because it is an European initiative. And now we are, anyway, that I told you before, in a sort of new Cold War, because 1 year ago, Indians, anyway, sent a lander on the South Pole of the Moon, and
Yes.
the mission was successful for the first time.
For the first time, yeah.
Humans, yes, sent a lander, and the mission was successful. Japanese tried before Indians, and the mission crashed. So, and Americans are pushing to build this system. So they are not only working on Mars, but they also want to again on the moon. We don't know what Chinese and Russians are carrying out, but surely they're working on it. So it's important having expertise and also new and young energies, because so it's important also, no, having enthusiasm from young engineers in this program.
That's amazing, because I mean you are touching for the moon everything that we have already learned in the master, like the rover part, the terminal, the signals, the system part, the ground segment, the space segment. How do you have to design everything from scratch, right? Trying to reuse as much as possible the technology that we are using on Earth in the moon in order to speed up all the development process, right? But also implementing some novelties in technology that have been maybe already proposed by Americans in the past and are working today, and also with the interoperability and also the help or let's say the cooperation of different countries. I think it's an amazing.
Yes. And it's important also anyway to maintain the schedule, because otherwise we lose credibility, no? Because we are talking NASA and JAXA, we want to have this interoperability test, and it's important to maintain the schedule. In the meantime, we should face these issues and new topics we should solve, because also navigation of the light is based on a small platform, guys. Is not the Galileo satellite,
but
first generation and the second generation satellite. We have only a very small platform.
You know that in 2-3 weeks we'll have here in the Academy Steven Bouchiret, that may know, right, from Galileo second generation, and he's trying also to push the agile development of the Galileo second generation to do it faster, let's say, right? This is the idea, not to go
faster.
Yes.
But anyway, they have anyway knowledge, and they have also experience from the first generation. And before they had GPS, but in our case we don't have any reference. We can use anyway Galileo, but it is not the same, because as I told you before, the DTS concept that it is crucial for navigation is different. Yeah, there is a reuse only on timing part. But so MSPA is new. Also, the satellite is small, and we should host on board a small compact navigation payload. And also, you should have these MAJ antennas to be pointed towards Earth to establish the link. There is the topic about the propulsion. We are proposing electrical propulsion, so it's a challenging topic. And also, we don't know the environment. What is the impacts of lunar environment on shielding of the satellite? For the first time, we are launching a satellite with anyway a lifetime of 6 years, not 1 year, 6 months. So there are a lot of topics, and I'm a system engineer, but so having experts on different topics is so important, working together and trying to solve anyway, define a baseline to be adopted. Surely we are lucky because we launched only the first satellite, 2028. We have at least 1 year and a half to understand. So anyway, the potential problems, the potential issues, to tune the barriers inside SPF, also to calibrate the entire navigation payload chain. So we for this reason, is better sending only one satellite at the beginning, because it could be a sort of lesson learned also for the other 3 satellites, no?
Exactly. Well, I think we can finish soon now. Thank you so much. Maybe you have maybe any question, just that you can just I think it's the time to ask to Cosimo. He's an expert, and you can see in everything he's able to talk about the rover, the system, the orbits. I think you have been working in everything, right?
We should work on it. I'm a system engineer, so I'm trying to cover all these aspects. Surely I'm not an expert on each discipline, but as you know well, so if you are the system anyway principal navigation engineer, you have the entire picture so clear in mind, because otherwise, so then
you're lost.
Problems, no?
Exactly.
Like when I work at Italia Space, there is a famous famous motto.
Quote.
So
Yes.
If you don't work well and the navigation satellite launch will be failed, you will have the same ending of Spartacus, because Spartacus, no, the rebel against the Romans, was crucified along the Appia by Romans, and so this story was in ways very famous among Romans.
You will be a martyr in the future. Don't
Yeah,
I hope you.
yeah.
I hope nobody will sacrifice you. Don't do
Yeah, I'm joking, but sometimes to my managers in the past, you know, in order to put pressure, they say that. But I'm joking about it. Yeah.
Okay. Okay, if there is no questions, maybe we can close now. Yes, you have a question, Matthias. Where is Cosimo? I just lost him. You see him? You're here. Yes. Go ahead, Matthias.
Go ahead.
Yeah.
Yes.
First of all, thank you a lot, Cosmo, for your time and for the talk. It was really interesting. I just had a question in mind. It's just out of curiosity. Is there any other approach being considered for the orbit determination for the phase where there will intended to be global coverage? For example, accounting for satellites that would be on eclipse for direct to Earth track.
Yes. In our architecture, no, we have defined these 3 TT&C stations distributed so with the longitude 120 degrees among them, in order, to increase the visibility of the satellites from Earth. We made also a lot of visibility analysis simulations to understand the potential impact when satellites is not visible. Anyway, we have some gaps in the visibility, but up to 2 hours, these gaps are tolerated, because anyway you have the CSA of 10 meters up to 2 hours. If you have a gap higher than 2 hours, you have a degradation of your performance. Anyway, if there are some eclipses, so you cannot talk with the satellite, surely, but according to our results, so 3 stations are enough to have a very high visibility of satellites from Earth, and also ensuring the performance required by SRT level. Is a very good question. We worked a lot on that before finally selecting the baseline. But probably in the future, when you should also address the full coverage, so for the next generation, probably having inter-satellite link between satellites can be very useful to enable a very high accurate orbit determination process. Sure.
Good.
I have a question.
Go on.
And it's regarding, so you mentioned that you work very closely to other agencies to ensure there's this interoperability issues for that will help for everybody to the technologies are compatible and everything, but at the same time there is the own interest of every agency to with their projects. So for example, if there is a better spot for a satellite, who gets to decide who gets it, or is there another organization that tries to solve this diplomatically, or how do you do this communication in collaboration but also in competition with other agencies?
Yes. First of all, in this working group, because there is a Lunar PNT working group, there are other working groups, system, security, communication. There are a lot of working groups that are led by these 3 agencies. We are discussing these different topics, but anyway, there is a high-level working group. So for this important question, like for example, how we can anyway give the different PRNs to the satellites of the different constellations. Which kind of reference frames anyway should be adopted, so which kind of approach we can use to validate anyway the CISE of the different constellations, because if you want to use data systems, you should be sure that the CISE, that anyway can be achieved by the other constellations, is in line with your number. So all these aspects are addressed in high-level meetings in order to avoid that
incoherencies.
Only one of these agencies is taking the full control. But concerning aspects about the implementation of each infrastructure, we don't enter to these details, because we have different industrial consortium, and each industrial consortium is designing its solution independently from others. What is important is to have interoperability using the same signal space SED, using the same reference frames, also having a own PRN for each satellite, and that's all. Not entering in the details of the implementation of each technology, because we are adopting different solutions, but what it is important is that the navigation signals broadcasted to the potential users are compliant with the FS signal spaces.
It's more or less the same as we have today with GPS, GLONASS, and so on. We have high-level meetings in order to make sure that everything is interoperable and your receiver is able to track, to process all the signals, right, without any, let's say, interferences or, let's say, affections or impact, right? Then the idea is this, yes. Okay.
As you remember, when the POC modulation was invented, the reason is that you cannot use BPS key, because otherwise you have an overlap on the GPS signal, and you invented the POC in order to have these peaks that are shifted by the central peak of the GPS L1 signal.
But this was as a common agreement as well with the Americans, right? When we
designed with Americans, In our case, no, because we are broadcasting the same signal, so we don't have any interference.
Exactly. It's the CSICD is the same for everybody, which is the
same for everybody.
Exactly. Well, A last question maybe? Who wants to go to the moon? Okay, anyway, thank you so much, Cosimo. It has been very amazing. I think we have to
Thank you
review
very much.
review everything, all the talk, because you share so many concepts. But at the end, if you have a look on the system architecture and so on, regardless the new novelties and so on, but the system, the ground segment is more or less the same as the Galileo 1. I mean, the different elements that we can find, and we can identify the same, let's say, concepts, let's say.
Eduardo, one question from my side. Are you also organizing the summer school with ESA, Jersey this year in July?
I was invited. I was in Greece. You mean in Greece, right?
Greece, yes.
Are you going?
No, probably Xavier is coming.
Javier.
Xavier, yes, is retiring this year, but
yes,
probably he's coming. Yeah, he's coming.
I will be having lunch soon with him, because he's living in Toulouse. Well, sometimes he's here in Toulouse, right? Even he's based in Toulouse, let's say. And yes, I'm not coming. I mean, I was invited, but I'm not coming just this year to Greece. Yes.
In July, I will be very busy with PDRs, and so probably I cannot come. But Xavier is coming. Yes.
Very good. Anyways, if you want some support to filter your reads and to make some reads to the industry and in the PDR, we are 30 people here, and we can help you to make reads. Okay.
To make reads. Thank you, Eduardo. Thank you.
Okay, thank you so much, Cosimo. Bye, everybody.
Thank you. Bye. Yes.
Bye.
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 Thank you.
Bye.
Thanks so much.
Going to the moon was the first step. Staying there is our next ambition, with dozens of international public and private missions setting their sights on the lunar surface in the coming years. But the technologies we take for granted here on Earth, satellite navigation systems like Galileo or GPS, video calls, or even fast file transfer, are very limited on the moon. Since the Apollo program, very few lunar missions have managed to land successfully. We cannot have a sustainable lunar presence without reliable and autonomous communications and navigation. That's why ESA is working with its industrial partners on the Moonlight initiative to become the first off-planet commercial telecoms and satellite navigation provider. Launched into space, 3 or 4 satellites are carried into the moon's orbit by a space tug and deployed one by one to form a constellation of lunar satellites. These relays connect to Earth via 3 dedicated ground stations, forging a data network that spans up to 400,000 kilometers. The constellation's orbits are optimized to give coverage to the lunar South Pole, whose sustained sunlight and polar ice make it the focus of upcoming missions. Moonlight will provide data capacities sufficient to serve these planned and future missions over the coming decades, with a navigation service that enables accurate, real-time positioning for all lunar missions. This is the Argonaut. This, or any lunar lander, could greatly benefit from the Moonlight program. With a simplified navigational subsystem, our lander saves mass.